Cool. Well, thanks for having me. I'm Ben, and today I'm going to be talking about building a real-time video processor with Swift and Metal. So briefly about me, probably review if you saw yesterday, I work on Spectre with my partner Sebastian, and it's an app that allows you to take long exposure photos with your iPhone, and this involves obviously a lot of real-time processing. And this is actually our second app. Our first app was Halide, which is designed for pro photography and manual photography, although there is a major real-time rendering component in features like our depth capture. This is similar to the portrait mode in the iPhone. What's really interesting about this mode is that we're actually merging multiple video sources together, the color data and then a version of the image that's blurred, and then we composite the two using depth data that's coming from the system. So I'll be touching on this example a few times in the presentation so we have something concrete to work with. So the structure of today's talk, I'm going to be talking about the architecture of a real-time rendering app. I'll be talking about the performance considerations and then the nuances of working with image data because it's a lot more complicated than reading and writing red, green, and blue data. So I have a lot I want to cover in the time, so I'm just going to dive right in and talk about architecture. So I'm not going to read line by line Apple documentation. I don't think that's a really good use of our time. I'll just say that it all starts by hooking into a delegate method in AV Foundation and saying, please deliver me video frames off of the camera, or please deliver video frames from a movie source or what have you. And then you start receiving frames one by one as the system processes it. And you're going to develop a core rendering loop where you receive frames from the system. Depending on what your app does, you are going to be updating internal state in your app. And then you are going to issue commands to the GPU, either to perform visual effects, to do merging of different images, but ultimately to render the video frames back out onto the screen. Now, if anyone here has done game development, this will seem very familiar to the core render loop in a video game, where that's driven by a timer that fires 60 frames a second. Fortunately, if you're working with video, you're probably only dealing with 30 frames a second, unless you're doing some high frame rate video. So the good news is you have an amazing 30 milliseconds per second to do all of this logic and then render out to the system. So that's not a lot of time to work with, so that's why we're going to be touching on performance in a bit. Most of your work for the first part of this loop is going to be done in Swift. So you're going to set up a render state, you're going to set up the GPU commands, and then you're going to dispatch that work to the GPU. The actual code that gets executed on the GPU is run in what's known as a shader. A shader is a tiny program that's run massively in parallel on your GPU. When I say massively in parallel, I'm talking about hundreds of threads running in parallel, one thread per pixel on your image. It's written in a language that's a subset of C++11, which Apple has branded Metal, and we'll touch on that in a short bit. I think most people in this room probably do more front-end development. You maybe connect to web services, and so you're probably already familiar with Swift or Objective-C. So I think the more interesting bit for people is going to be the GPU side of things, which will probably be new to a lot of people in the room. So I'm going to go a bit into depth here. Now, when you're working on the GPU, you actually have a choice of two different systems to work with, depending on what you're trying to accomplish. The first system is the compute pipeline. And this is very straightforward, and I'll touch on that first. The second system is the 3D pipeline. Now, GPUs were designed originally for 3D rendering, like video games. And so that's a little bit more complicated, so I'll touch on that shortly. But let's start by just showing you what a very simple hello world of shaders looks like using a compute pipeline. And by the way, compute pipelines, unlike the 3D pipeline, they don't just have to be used for graphics. They're a general purpose GPU programming language. You could use it for mining cryptocurrency if you want, but we are using it for images here. So here is a hello world where all that we're doing is we're reading in bitmap data from one bitmap, and we're writing it out to another bitmap. Section by section here, you'll notice that it's referred to as a texture. For now, consider texture the same thing as a bitmap. I'll go into detail. And notice here there's this GID, which is the basically the position in the image that we're working in. You can think of it as the X and Y coordinate. So all that we're doing is we're taking the first texture, we're reading in the coordinate using .read, and then we get this half 4 value. Half is a half float. And then we take that same color data and we just pass it on to the output texture and writing it in the same position. So this is about as simple as you can get. It accomplishes nothing, but that's what a shader looks like. So how do we execute this? In the Swift side of the code, I've taken out all the boilerplate to show you exactly what it looks like, the important bits. You start out at the beginning of your app and you declare the different shaders that you want to execute. So here I say that I have this function called hello world that I want to execute later, and I make a handle that references this shader, which is known as a state, a compute pipeline state. I store that somewhere. Then later, inside of my run loop, I say, OK, configure the GPU to execute this program. And then I execute this dispatch thread groups method at the bottom, and it dispatches it. Notice that I have those two calls there, set texture, which sets the textures that I want to pass to this function. How exactly does that link up? Well, you'll notice this annotation in the shader that I showed earlier. This is not standard C++. This is particular to shaders. This double bracket notation lets you annotate the different parameters so that the compiler knows how it maps to the functions as we're gluing things together in Swift. So here I marked it saying this is texture slot 0. And then in that encoder that I showed a moment ago, I say set texture input image at index 0, and then it will be properly bound together when the shader executes. Okay? So that's the basic of gluing it all together. The 3D pipeline is a little bit more complicated, and you're probably saying, then why are we using it? And if you read Apple's documentation, they tell you that the 3D pipeline is the most efficient way of displaying content on screen. When your GPU knows that you're not reading and writing data to textures, it can take the fast path. It can take shortcuts because it knows it's one directional. So in the 3D pipeline, you really want to use this ultimately to render content to screen, or there's some other cases I'll show in a little bit. Now, fortunately, you can render similarly to the compute pipeline using the 3D pipeline by rendering the world's most boring 3D model. All that we do is we pass 4 vertices to the 3D pipeline saying, I would like to render a flat plane on screen. And on that flat plane, I will render the image data that I had earlier. So again, it's the world's most boring 3D model. The 3D pipeline actually has 2 stages. The first stage you're going to skip, but it's known as the vertex stage. So if we were rendering a complex 3D model, we'd have all of these points that make up a complex bunny model, like here on screen. And I'm not going to review a graphics class, but usually when you're rendering a 3D model, you have to transform all these vertices relative to the camera and do perspective transformations, which you don't really have to do if you're just rendering flat 2D data. So we usually just skip this first stage unless you have something clever you want to do. And then you execute the second stage, which is known as the fragment stage. And this is when you would shade your 3D model. Now, I should say that in the texture stage, your shaders actually run once for every vertex in your 3D model. In our case, it'll be run 4 times. And in... Oh, I'm sorry. I've been hitting the next button. All right. So in the vertex shade stage, the shader would run 4 times, 1 for each vertex. But then in the fragment stage, it gets run once for every point on the surface of the image. So every red point in that bunny model, the shader would run once for every pixel that makes up that image. And usually, if you're doing a 3D model, you'd use a sophisticated algorithm to simulate a matte surface or a glossy surface or a reflective surface or what have you. And again, you don't have to get that sophisticated if you're just rendering a 2D image. Now, one more thing I want to touch on is I said earlier that we refer to bitmaps as textures. It's a little more complicated than that. Textures are actually a more powerful abstraction around working with bitmap data. The reason they're called textures is it goes back to when you're rendering a 3D game, you think about texture maps. So they were designed for rendering textures on 3D models. But there's actually dedicated hardware on your GPU for working with texture data in an accelerated way. And you can do lots of techniques that are really, really fast that you can't do on a CPU. Now, for example, imagine that you have an image that's just a checkerboard pattern where every pixel is black and white. Now, if this were just an array of arrays, you'd only be able to read the discrete color values at each coordinate, right? You could read 0, 0, or 1, 0, and you'd get black and white data. But what would happen if you wanted to read like a floating point value in between, which you're going to want to interpolate between these values all the time, like if you're enlarging your image or if you're rotating it and you want to anti-alias it. Well, when you're working with textures, you can actually say, I want to sample this floating point in between those two values, and the hardware will automatically filter it for you, which means it will blend it as a gray. And you can do more sophisticated filtering and all sorts of other techniques. But this is just one example of why a texture is like a super powerful bitmap. So when would you want to use the compute pipeline versus the 3D pipeline? I mean, as I said before, the compute pipeline was way simpler. And if you're doing something like you're building an app like Lightroom or you're doing simple 2D image processing, the 3D pipeline might be overkill. Well, as I said before, it's going to be faster to get stuff on screen, so you'd want to consider it there. But also, if you're doing complex compositing, for example, on the right is the group FaceTime view on iOS. It's probably drawn with UIKit, but imagine for a moment you wanted to draw that using the GPU. What's nice is if you were to render each image there as like a flat plane, using the GPU, and you let it composite it using the 3D pipeline, your GPU can take all these shortcuts. So for example, notice that some of the images overlap each other. The GPU can recognize that a portion of one image is occluded. It's blocked by another image, and it will discard the geometry underneath, which will prevent what's known as overdraw, which is very bad, where you're doing a bunch of rendering that just gets thrown out, so it's a big waste. The GPU has a pipeline in the hardware where it'll just throw it out and never run that shader for you, so it takes a fraction of the complexity of trying to write that code yourself to optimize it. In fact, if you tried to do all this with a compute pipeline, you'd just be reinventing the 3D pipeline and probably worse than what the hardware could give you for free. So if you're ambitious and you want to rebuild UIKit yourself from scratch, you're crazy, but you'd probably want to look at the 3D pipeline and it would be able to handle it for you. Cool. Now I want to touch on a couple of cool things about Swift that work very well for doing 3D rendering with shaders. So the way that you pass data between the CPU world, like Swift or Objective-C or C++, and the GPU shaders is using data structures in structs directly. So it's very position dependent. So you might bundle together in your data in a C struct. Now, what's not nice if you were to use, say, a high-level language is that you'd need to write the data layout twice. Once in the high-level language, and then you'd have the C struct in your shader code, right? And if you forgot to update a field between the two, everything would break, and you wouldn't know why. And it would be very frustrating. But what's really cool is because Metal is a subset of C++, you could define this struct in a header, and then import it into your Swift code directly and use it just like any other Swift struct. So you keep everything in sync. You can even use nice little methods on there like the initializers, just like with Swift structs, and it all just works. It's really nice. And one other nice thing is that Swift was designed around performance to begin with. So it has affordances where you can have syntactic sugar without having the same hit on performance of, say, a dynamic language. So for example, in Swift 5.1, they introduced function builders, which is the basis of Swift UI. I've been playing around with developing for myself a similar domain-specific language for defining how the shaders and their parameters bind to each other. So rather than use the imperative style that I showed earlier, I can just say, well, I want to pass my vertex shader these buffers, and I want to pass my fragment shader these buffers, and it cuts a bunch of boilerplate and makes the code a bit more clearer to read. So that's pretty cool to work with. Now, one last thing that I want to talk about to transition to our next section. All of the code that you're running in Swift is, and then dispatch the GPU, all the GPU code is run asynchronously. Okay? There is latency between when you execute, when you kick something off with a GPU, they have to spin up hundreds of threads, and then it could take, say, a millisecond or two before it returns. And you want to make sure that it is asynchronous. You do not want to make blocking calls in that core run loop because, again, you might have only 30 milliseconds to work with. So you never want to block your core run loop, although there are methods to do it. You know, if you're doing something that's non-real-time, maybe it would make sense to use it, like if you were doing an image editor, but highly not recommended. And in fact, another issue here is that you have a limited set of resources. So as you're running through this core rendering loop, you are getting frames in from the system, from AV Foundation. You want to pass it through your image processing pipeline. And then once your shaders execute, you want to release all of your resources back into their pools so they can recycle them. Now, why is this so important? Now, let's do some math. The iPhone can give you 12.5 megapixel images off the camera. 12.5 megapixels. That's not 12.5 megabytes of memory because each pixel has 4 color channels. You don't have to be a math major here to do the math. What's 4 times 12.5? Just under 50 megabytes of memory per image that's coming in from the system. So if you were now getting 30 frames per second, it would only take a few seconds of this data being backed up before you run out of memory and your app crashes, right? So in practice, there's a technique known as double buffering or triple buffering, where maybe you'll keep, say, 3 copies of buffers around. So that's only about, what is that, 150 megabytes? But you're then recycling it, and that's just to ensure you don't drop frames. If you make a mistake, everyone might get their system backed up a bit. So you still have 1 extra buffer to work with, but you generally would only have double or triple buffered for memory reasons, right? And you always need to be recycling them. So imagine this like UI table view cell recycling, but with much worse consequences if you make a mistake. So that brings us to our next section, performance, and really understanding how to make things fast, and that's half the battle. So as I said earlier, you're going to want to update your state inside of your run loop inside of the Swift side of things. Now, what are some examples? Well, it's app dependent, but in the case of Halide, the values that we get for that depth data are unclamped. They're actually in distance values. So they might actually be referring to, say, a meter or 3 meters, which is greater than 1. So if we use this data directly without clamping it between 0 and 1, it's not really usable, right? So as part of our process, as we receive these depth maps from the system, we find the minimum and maximum values of the depth map so that we can pass to the shader and properly set the proper distance ranges. So that means iterating through possibly 10,000 pixels in a very short period of time. And that can be fast. Another example, a few years ago, I did some contract work for Periscope, and I built a real-time sketching system for their broadcasts. So what you could do, this is from the launch video, is you could draw on the image to highlight something, and then after a few seconds, the drawing would disappear at the same pace that it appeared. It's clipped a little in the product launch video. So in this situation, we might be dealing with thousands of points that the user has touched. We need to render them, and we need to keep track of the life of each of those points. So after 2 or 3 seconds, after the point has lived on screen for that period of time, then it needs to enter a decay state and slowly fade away. So potentially with each frame, we could be dealing with thousands of points that we need to be checking and updating like a particle system. Okay? Now, even if you aren't dealing with any of that, a concrete reason to understand it is that it prevents you from overstressing over small things, right? A lot of engineers don't know what systems are fast at doing, right? And they think that, oh, I can't do this because it'll hurt performance. But most people don't understand where the true bottlenecks are on modern computers. And so that's why I want to touch on the most important graph that engineers don't know about. This graph above is how much faster CPUs have gotten over time, thanks to Moore's law. Moore's law has not been so generous to memory. And so while CPUs have gotten faster, memory has mostly stayed the same speed. So your bottleneck today is likely not your CPU. It's your memory access patterns. Okay? But wait a minute, you're thinking, but well, my computer feels so much faster than 20 years ago. And the way that computer engineers have architected around these bottlenecks is through memory hierarchies. So what is that? Well, your CPU has really fast memory built into it, right on the die, and that's known as L1 memory. Okay, there's very little of it for a number of physics reasons, but if data is in this L1 cache, then it's very fast to access. But as you start loading more data, it will likely fill up this L1 cache and then start pushing data as it's evicted to L2 cache, which is further away from the CPU. There's more memory in L2 cache, but it's slower. And as you page in more data, L2 cache fills up and it moves to L3, and then you might have L4, or it might then go to main memory. Okay, well, let me give you an example of the different speeds you can expect from these different levels of memory. Let's say, by the way, I just want to credit, this is a demo from Scott Myers, who's a noted C++ expert, and so I'll link to his full talk later, but I'm totally stealing it because it's awesome. But let's say that you're accessing L1 memory, and it is this fast. Okay, it's not really that fast; it's much faster. But let's say L2 is relatively this fast. Oh, okay. Well, if L2 is filled up, L3 takes this amount of time, and if it's not in L3, it's in main memory, and this is where you go grab a coffee, you check Twitter, you call your parents, check how they're doing, maybe go to jury duty. I don't know if you have that out here, but you just sort of get your errands done, and then maybe your data will be available. Okay. Now I said that there's very little memory available on with each level of the hierarchy, and now for the numbers. This is all using the iPhone 6s. So obviously newer devices probably have a little bit more, but most iPhones have these different levels. L1 has 64 kilobytes. That's not a typo. That's kilobytes of memory in L1. L2 is 1 megabyte, and that takes 10 cycles, so it's about 2.5 times slower. L3 has 4 megabytes, and that takes 40 cycles to access. Main memory has about 1.8 gigs, and it takes 120 cycles, which is about 30 times slower than L1. So if there's a lesson here, is that you want to organize your data with locality in mind, so that you can predict and make sure that you're not constantly fetching data that's not in the cache. And I won't get into even deeper detail and talk about cache lines, but the way that your CPU can prefetch. But there's this whole movement, especially in games, around the idea of data-oriented design. And that's where you arrange your data in a way that works with the CPU so that it can prefetch data before you need it in an efficient way. As much as we love to talk about big O and different algorithmic complexity, that's only half the story. And in fact, the most efficient data structure you can use is an array if you're processing a lot of data. Just set up your data in an array and let your CPU run in a straight line, and that's the fastest way you can process batches of data. For more details, check out Scott Myers' talk. And also, Mike Acton is a proponent of data-oriented design. He's a former engine director over at Insomniac Games. He now works on Unity's engine. He's an engine director there. Really awesome content. To answer the next obvious question, is there a way to measure it? There is a counters instrument in Xcode. That's a good starting point, which is built on top of dtrace. But to tell you the truth, if you're at the point where everything is slow and you're trying to instrument it, it's the last step, you're already doomed. This is something that you need to have in the back of your head as you're architecting the app. But the good news is it doesn't involve having to be writing assembly, and it could be as simple as just keeping in the back of your head, how am I accessing data? So let me give you an example. Let's say that you have an array of arrays. This is an obvious one. I love it. If you access the array of arrays looping based on the orientation of the data so that it's working in the stride that you're accessing it linearly, versus if you switch the loop and you jump in the wrong order, One order, it works efficiently, where it's able to prefetch in lines and read it in an incredibly fast way, where the other, you're constantly bouncing around and you're not going to be getting any cache hits, and you're going to be working against the CPU. So in this example of reading depth data, just using the proper order of the loop is a quick 100 microsecond win, which might not seem a lot, but again, you're working with 30 milliseconds. So little wins like this quickly add up. And it doesn't require thinking in assembly, just thinking in the back of your head, OK, how's the data aligned? But let's talk about architecture, right? So this has implications of, let's say, you're building a game, like Stardew Valley. And awesome game, and it uses this tile structure to represent the game board, I guess you'd call it. Now, let's say that you need to represent this patch of wheat that you're farming. And this wheat grows over time. Now, how would you model this traditionally in object-oriented programming? Well, you start out with a wheat patch class, this opaque object that is encapsulate all the details, and you have a position attribute, and you have a height attribute, and because we're using object-oriented programming, we want to use message passing, so no, you don't go and reach in there and change its height value. No, you call a grow method on it in case you want to change the implementation later. And that's going to murder performance. Okay, object-oriented paradigms are terrible for performance. One reason is because they're generally located in the heap, and they're just randomly strewn about memory. So you're almost never going to get a bunch of these objects in a single cache line request. They're just randomly all over the place, which is going to blow out your cache. The second issue is that in many languages like Objective-C, especially dynamic languages, it's going to have dynamic dispatch. So you're going to miss your instruction cache. So in addition to the data, you also want to be thinking about running the same instructions over and over again, so it doesn't have to reach out to load instruction code. But just philosophically, it encourages you to think of your problems as isolated instances instead of the transformations. So for example, with that height loop, as we're going through all the wheat patch items and looping through them, you might be incrementing the wheat, the corn, the barley, but you'd want to arrange them all so that you're running the same code over and over again. And the more compactly you can put the code together, combined with the same loop of code, the more efficiently it's going to run. You should really be thinking about data. And Swift is a great language because it gives you explicit control over the data layout, like C++. It's static dispatch by default, similar to C++, unless you use virtual functions. And most importantly, it encourages you to think in terms of values instead of these opaque abstractions. So in contrast to the object-oriented design, on the right is the data-oriented design. You could represent that wheat patch just as an array of arrays that are each just a uint8. And the position in the array is implicitly the position in the world. This is a classic modeling mistake early game developers make, where they have these arbitrary attributes when they aren't necessary, the position, when the data itself could declare it. Now, this is a bit of an extreme example, and if you're coming from high-level programming, you might be thinking, oh no, well, what about my abstractions? This is madness. Well, let's start building up the lower levels here. Now, you can still use things like type safety. There's a pattern in C++ that I've heard called the strong type def, where you wrap these discrete values. Here we're using two values that we use in Halide, which, although they're both floats, you don't want to mix and match them. You don't want to accidentally multiply or add your F number, your aperture, with your ISO. It just doesn't make sense, but it would be a type of bug that you might run into if you have a typing error and you're doing some multiplication and you don't have type safety. A normal type def doesn't give you that protection, but here with a struct, the compiler will optimize away the struct, and it'll be just these discrete values that are in memory, and the compiler will catch errors for you. Okay, but what about higher level shared behavior and abstractions? Okay, so I think everyone here hopefully has played Super Mario Brothers and our friend, the Koopa Troopa, or his evil sibling, the one that bounces around with wings, okay? They're mostly the same, right? Until you jump on one of them and it becomes the other. So you don't want to just cut and paste that behavior everywhere. And if you're used to object-oriented programming, of course, the solution in game development originally was object inheritance. And in early game development, when they were trying out OO, they would run into, well, we have these missile objects. Well, we have different types of missiles in our game, so let's subclass there. We have different types of spaceships, and you have a very deep hierarchy. But then what happens when you have several cross-cutting behaviors, where you have the Goomba, who now they want to have bouncing around? Ugh. Okay, well, then your class hierarchy starts looking like the attributes, and it becomes like this horrible, like, multiple inheritance, or the diamond pyramid of doom they call in OO. Which is why, if you've been around the block, you might have heard favor composition over inheritance. So game developers who were burned by this early were like, yeah, no, okay, we're not going to do any of that. And they came up with a system where you can emphasize behaviors without inheritance, where you can focus on these components and systems. And I'm not going to go into a lot of detail here. There's excellent other talks if you're interested in this. But in game development now, the current best practice is what's known as an entity component system, where you have discrete components and systems like, say, physics systems that operate on discrete data. And I'd say OO is mostly dead in game development in favor of ECS. But even if you aren't interested in any of that modeling, one last thing I want to touch on performance is you could think of data-oriented design as a way of thinking. So let's say that you have this image that you want to blur. In our case, like we have the portrait blur, where we want to have a very large blur radius to simulate the blur of the bokeh of a camera. Now, if you want a rich, beautiful blur like this, it is going to destroy performance, because the computational complexity of a Gaussian blur is big O of n times r squared, with n being the number of pixels and r being the radius, which basically means that the larger the blur, it's going to rocket shit up as far as how it's going to affect performance. Now, one solution is that you can seek out a linear, algorithm that blurs in linear time, and there are approximation of Gaussian blurs, but a lot of them show rendering artifacts. Like there tends to be like jagged edges. And UIKit uses some of those cheaper algorithms, and most users never notice because you're just like blurring in the background in UIKit. So it's fine, and that's great. But in the case of like an image processing app, we want a really rich, beautiful blur like this. Well, what if we downscale the image to 1/4 of its size, and then blur it, and then use hardware to upscale it later? If I didn't have the labels at the bottom of the screen, there's no way you could tell the difference between these two blurs. It's good enough. And in addition to not just processing 1/4 the number of pixels, the blur radius is now half of what it would be at the full resolution. This is an easy win. It didn't involve a single line of assembly. It's just a way of thinking. Cool. So great. You've architected the perfect app. You've got all those UML diagrams, and it's ready. You've got your shaders set up, and now the exciting part. Let's get these images on screen. So here's the image that we're pointing our camera at, and we're expecting this, of course, to appear in the viewfinder exactly like what we took a photo of. And instead, you get this. Huh. It's almost as if two color channels are missing, and we're just getting the red color channel only. Well, that's because they are. It turns out that this system is not delivering you a red, green, and blue image. It's actually delivering you two separate images. One of them is one channel, and the other image has two channels. And this is what's known as YUV color encoding. And this is the default when you access color data from the camera. And I think if you're reading movie files, I think it prefers this. Now, the luminance, or you'll hear Y, the brightness value, that's one image, and that's the grayscale. And then the other image is the color values, chromaticity. That's the UV and YUV. And what does the UV stand for? Well, those color values are positions in this chart, this Cartesian color space, with the U and V refer to where the amount of blue and the amount of red, right? They're coordinates somewhere on this graph. If you'll notice, sometimes it's referred to as YCBCR. CB stands for color blue. CR stands for color red, which are the two axes here. So they're both, unless you talk to an image processing nerd, they mostly mean the same thing, and they're used interchangeably. Now, why would they do this to us, aside to frustrate us and ensure that graphics programmers have job security? Well, has everyone here seen this optical illusion, maybe floating around Twitter or whatever your chosen meme source is? So if you've seen this before, it turns out that these people don't have colored shirts. These shirts are actually grayscale. It's just in the image, there's this cross-color pattern. And our eyes are actually filling in the color detail. And this is an optical illusion because our eyes are more sensitive to shifts in luminance than they are in color. Our eyes will naturally fill in the details there and think that they're one specific color. Obviously, we wouldn't throw away that much color, but wait a minute. What if we take this image that has one color channel, two color channels, and we actually store a version that's 1/4 the size? This is happening in most of your image viewing on the web, and you can't tell the difference until I just told you now. And by the way, since that image on the right is a 2-color channel image, we're actually in total saving 50% of the memory. We're passing around 50% of the less data. We're processing 50% less data. And so as we showed earlier, if your bottleneck is memory, this represents a huge win for a little cost of then at render time, we just have to reassemble it together when we go to render it on screen. The good news is it's as simple as copying and pasting a shader. The bad news is Apple isn't really good at showing you where the shader is. They don't put this in any of the metal docs, but this little shader that you cut and paste is actually an ARKit, because ARKit only passes you data in YUV format, and no doubt they've had tons of radar files, like radars filed, asking, hey, how do I work with this? And so they give you this sample code. It's not that bad. And you just use that, and it'll reassemble it. One last thing I want to address about YUV is you'll hear some numbers thrown around, like 444, 420, 422. There's not going to be a test on this, but those just refer to the amount of the ratio of how much data is thrown out. So typically you'll see 420, which means 3/4 of the data is thrown out, and the different ratios refer to the different ways that you can subsample the data. So that's why if you go through the documentation, you can configure how you want data passed to you. And the default is 420, YCBCR, 8 biplanar full range, which we don't need to get into. But those numbers at the beginning are not encrypted. That's what it all refers to. That said, here's a secret I shouldn't tell you, but you can request RGB data, but Apple will not default to it, and it's not recommended because you're going to be passing a lot more data around. So you're probably better off using YUV if you're dealing with 4K, although sometimes you do need to convert it to RGB because of how you're setting up your rendering pipeline for later. So it's very easy to get messed up with all this because the textures that you're passing around don't mean anything. They're just raw image data. So there's no meaning behind it. Like as we showed earlier, you could get confused and not realize you're supposed to be assembling these two textures to make the RGB image. So I create a wrapper in Swift where I have an explicit struct so that if I pass an YCBCR struct, I get both of those textures together. And that way, if I forget to write a shader to support RGB or YUV, the compiler will catch it for me, right? Cool. So we got red, green, and blue. And then we go to display it on screen, and then it's too dark. Well, what's going on there? So I hope everyone loves optical illusions, because we got another one coming up. Now, if I asked you to imagine a linear gradient from black to white, like a perfectly evenly distributed one, you probably imagine something like this, where if you had 0 to 255 values, and you wrote a loop, and just displayed on screen these pixel data, you would think that 128 would sit right in the center. In fact, the top image here is what a true linear gradient is as far as RGB data, or as far as luminance data. The bottom one is a perceptually linear gradient. Our eyes are more sensitive to shifts in shadow than highlight. In fact, if you were to just write the for loop and you wanted something that's perceptually linear, 128 would be way over on the right end, And all of the data that our eyes are more sensitive to would have to fit into that 128 value, right? But the problem is we've lost now so much data in that low end, right? By the way, I'd like to compliment the people running the projector here, because this is the first time I've been able to show this graph or this image, and you could actually make out the banding in the middle gradient there. Normally you have to click on that link at the bottom or load it on your laptop. But what would happen if you were to try to store data with a 128 over on the right side is that you don't have enough bits to really put all the precision in on the gradient in the center there. So you start seeing banding in the shadows because there just isn't enough precision. I usually, when I'm showing this on other projectors, I have that I boost the gradient on the lower part there just to show people, but you know that's might accentuate a little bit more of the banding, but it's not necessary. So how do we deal with a loss of precision and not having enough bits? And this is now the most difficult, frustrating thing for people who are starting out in graphics. Gamma. This thing that you have no idea why it exists in your system settings. Why am I messing around with this slider? Well, the purpose of gamma is that you have linear values, say, in real life. So when you take a photograph, life is linear. It's just these values, right? But when you store it in a file, you have only a limited set of numbers. So what you do is you kind of make it brighter. You boost it a little bit so that you have more bits of precision devoted to the shadows. So when you store it in a file or in data, you boost it up there, you gamma encode it, which if you were to then read those values directly without correction would make it look a little too bright. Your monitor then does the opposite when it's time to display it on screen, where it converts these gamma encoded values to the opposite. It decodes it that makes it look correct on screen. So as the final step of the process, it does this decoding and everything looks correct. But you need to understand what's going on because you're often going to be dealing with data that had that first curve applied to it, which will really mess up your math. So this is a popular example, and you should check out the link at the bottom, because there's so many image processing apps that get gamma calculations wrong, where they think they're dealing with linear values, but they're actually pulling data from files or from the camera, and it's already gamma encoded. And then when you do the math, thinking this value is 1, this value is 0, let's blend it 50%, your math is wrong because they're actually both gamma encoded and your calculation's wrong. So here's an example of like, you expect this image that has these scan lines when it resizes to be the image, you expect it to look like the image in the upper right, but I believe this is Photoshop, an older version of Photoshop that people paid for. And it would actually destroy the image and turn it into this gray square. This is a common bug, and it's really, really common. Like there's examples of like font anti-aliasing. They do the calculations wrong. And Photoshop for the longest time had a bug with the brushes where they would composite it and you'd see this black fringing on the bottom because they were compositing it based on the incorrect calculations. In fact, Photoshop for a while had a checkbox to preserve this behavior because artists were so used to it. So even when they fixed it, they're like, okay, well, we don't want to break anything, so here. So there's an awesome link at the bottom, what every coder should know about gamma to really understand it. But the real takeaway is if you run into bugs like this, is don't try to fix it by tweaking values. This is a common issue in 3D rendering where people will have like, they'll have a color model for like a light, and they'll notice the screen's really dark, like something's wrong here, and so they'll adjust the lighting inside of their game, which is not what you're supposed to do, because then you're not really fixing the problem. It's like fixing a broken test by commenting out the test. It's not going to end well. So you don't want to do that. And again, Apple's not great about exposing this, how to decode, but they have the Metal Programming Guide, which is about 200 pages long. It's a PDF that lays out the entire spec for the Metal shading language. Literally the second to last page, page 200, they have the snippet of code that you're supposed to use to gamma decode or encode it. They show both functions you're supposed to write. So you toss this into a helper function, and so when you pull in data that's gamma encoded, then you decode it, or vice versa when you go to display it on screen. So it's half the battle is just being aware of what you're working with. Cool. And so now there's one last thing, and this is a newer problem the last few years. And you go to display your image on screen, and if you have a very sharp eye, you'll notice the color's a little wrong. You might not notice it. If I didn't have this up here, this side by side, you probably wouldn't notice it. but the color's wrong. What's going on there? Well, there is no computer monitor in existence that can display every color in the world. This horseshoe pattern, this outer horseshoe, represents every visible color in the human visual spectrum. I mean, some people are gifted and they can actually see infrared, but that's very rare. And if you're a dog, you can actually see less. So I'm sorry for any dogs in the audience. But this is the human visual spectrum. And that triangle in the middle is what every computer monitor could read up until recently. This was our sRGB. This is the default color space of the World Wide Web. And then a few years ago, Apple went and released devices that could display more colors. They call it the Apple Display P3 color space, which is awesome when you actually see it. You're like, wow, the reds are so much richer. You can see so much more richer greens. Unfortunately, this is one more thing you need to keep track of. So if you aren't careful, say, when you configure your image pipeline, and you request data in wide color in this display P3, and then you display it on screen without configuring your textures and such to display wide color, then it'll be shifting these colors around, and everything will be a little bit off. It isn't that difficult to work with the two. Apple invented this sort of compatibility layer, which it calls extended sRGB. It's pretty cool. I won't go into too much detail, but it lets you specify values outside the range of 0 and 1 so they can play well together, but you just need to be aware of it. You need to be aware of the colors that are coming in and what color space they are, and you need to be aware of what colors are going out. And this is really painful if you're dealing with some devices that support wide color and some don't. So that earlier abstraction I showed you, I also have a color space property that sort of lets me tag if I'm working with wide color or not. And then in my shaders, I check, OK, is it wide color or not? And if it's wide color, I apply an extra transform to make things conform to the correct color space. Again, knowing is most of the battle. And there you go, the final image. So what did we cover today? We talked about the core render loop. We talked about shaders, how to focus on data, and that's most of the secret in performance. And we talked a lot about theory, YUV, gamma. Please, everyone in this room, please study gamma, and working with color spaces. And then you have a video renderer. Cool. So does anyone have any questions? Thanks.
So please raise your hand. I'll come up.
Hi. Thank you for the talk.
Thanks.
Can you please move to the slide from metal documentation with magic numbers, page 200?
This one here.
Yeah. Can you please, do you know, and if you know, can you please explain where these magic numbers come from?
Oh boy, this is everyone make sure you've had coffee, because I'm going to talk about BT601 and the Rec 709 spec. So a lot of these magic numbers come from broadcast standards. Some of them are North American, so check whatever local ones are. But some of them go all the way back to analog television. So those magic numbers are part of just broadcast standards for what are safe specs to work within, depending on television or with computer monitors. Some of the magic numbers are also kind of arbitrary, where they found that by giving a little extra knee or a little extra toe at the bottom, the top and bottom end, it creates perceptually better results. And in fact, there's debates in the graphics community when we switched over from standard definition TV to HD TV. We made some changes to the magic numbers, and some people were like, you broke decades worth of standards, and there wasn't that much of an improvement, which is why, in fact, it gets even more complicated, because Apple, in some of their video, the way they encode video, they use SD magic numbers, even though HD TV uses different magic numbers, which is the most Apple thing they could possibly do, right up there with, arbitrary power connectors, right? So, yeah, so they're kind of magic. They're based on usually perceptive, the way human vision works. And the good news is they tend to be standardized. So in the example earlier with YUV, you just copy and paste one color matrix, and it just works. So does that answer your question?
So I can trust them, and they will be the same.
On Apple platforms, and this is one of the reasons people ask us why don't we have Android apps? I can't guarantee that of all the devices they use the same values coming in from camera. I just don't know that space very well. So if you're an Android, actually this is the iOS track, so enough about that. Yes, so for iOS, until Apple very much announces at WWDC that they're changing numbers, like when they went to wide color, they'll forecast changes, so pay attention to those talks. But we've been able to preserve these magic numbers for several years now, and they've worked very well, and they just work.
Okay, thank you.
Thanks.
Hi, thanks you for the talk. I'd like to ask you about old iPhones and new iPhones. So I saw on your slides that that you should check on which iPhone your program is running, and so you should convert the data to sRGB color space or into P3 color space. And my question is about if Apple will invent some new displays that can provide you more colors than P3 does. You should add some new extension to your code to use these colors.
That's a good question, yeah, I think that it's inevitable because they're always going to want to sell a new model, and hardware is always getting better. But at the same time, again, one of the nicest things about iOS is that there's so many limited devices that we have to support. Although even now, I think we support like 10 different models. For the most part, trust me, when Apple supports wider color, they're going to make a big announcement of it. And at that point, the reason I use an exhaustive enum in Swift, which is my favorite feature when working with this, is when they invent the display P4 style. We're going up to 4. The display P4 color space, I'll just add an extra attribute to the enum, and then I'll deal with how the compiler's caught all the different places. Hopefully, I'm not accidentally hard-coding a value somewhere. I guess if I'm supporting sRGB and P3, I probably am not. But I'll just add another item to the enum. But I think that that's the thing that you have to balance as an engineer. Is you could in that example of that pixel format, I showed you 2. There are literally dozens of pixel formats, and only a fraction are supported on iOS. Tons of them are supported on Mac OS, and they support external monitors, external color sources. So you need to ultimately decide what is the range that we're actually going to support, and that's why I have my own abstraction over what Apple supports, so that I can catch of the devices that my app supports. This is my different paths that the code's going to traverse. So yeah, don't overthink it. But yeah, it is inevitable there will be more.
Thank you.
Yep. Cool.
Hi. When you were talking about game tiles, there was a slide that you showed a couple of structs within with one field within. Are there any reasons to use structs there instead of type aliases?
So type aliases are just an alias, so you don't get true type safety. I believe it's ultimately type aliases are designed just for readability versus actually the compiler catching that this is a different data type. I believe. I'm pretty sure in C it isn't. So type aliases are entirely, I believe, unless someone correct me. But if you have a type alias from earlier of f number and ISO, and I multiply them together by accident, the compiler will be like, okay, cool. Whereas if I actually wrap them in structs, it will complain and be like, this semantically doesn't make any sense, which is kind of like why in Objective-C, CG float uses this pattern, because on 32-bit devices, CG float is a normal float, and on 64-bit it's a double. So actually we've run into a situation, or if you weren't careful, then you might compile code for your 64-bit iOS device, move it over to Apple Watch, which is still 32-bit, and the compiler would be like, okay, cool. The trade-off is they don't have any of the affordances around CG float, which is why everyone in this room has spent so many hours of their life casting CG float to double and to these different structures.
So as I understand, you agree to pay some overhead for having structs in code, comparing to the benefits of type safety.
So this is an example of like, it shouldn't. The compiler should recognize this is just an underlying value, and it should optimize it out. I'm not an expert.
But it's not 100% true. It might be the overhead still.
Yeah, but on the flip side, if I were to represent that in something like a class, that would definitely have a huge overhead because there's no locality. I would say that the overhead of any kind of like, also it should be using static dispatch. So the overhead of using this should be marginal and probably not me worth fretting over. But yeah, so it's lighter weight. But if this were performance critical code, I would absolutely measure what the impact would be.
Okay, thanks.
Yep.